más cerca. Esta. Okay. Good morning, everybody. My name is Ferry Prins from the Autonomous University of Madrid. It is my pleasure to introduce today the first plenary speaker, Roberto Gómez. So this is the last day. We've already seen many sessions on revolutions that are coming. Without wanting to add to the hyperbole, today we're going to talk about the energy revolution. In this case, it's a revolution that is already ongoing, right? And I think it's good to be conscious of the fact that here in Spain we are lucky to be in the front row seat with, for example, just this year, the first 6 months, 80% of the electricity generation emission-free, which for a country of the size of Spain is really exceptional on the global level. In this first talk, we're going to get an overview, basically, of what is the role of physicists in this energy transition. It's my pleasure to introduce Roberto, who is a permanent lecturer at the European University of Valencia. He is not a physicist, which I think is even better to get the right perspective for us. He's trained as an industrial engineer, specialized in energy technologies, and he also a degree in economics from the University of Valencia. He has published extensively about the energy market in Europe, and without taking any more time, it's my pleasure. Roberto, the floor is yours.
Okay, thank you, Brian, for your introduction. I would like to thank the Spanish Royal Society for having invited me to give this speech. And today, I'm going to talk a little bit about the energy situation in Spain and in Europe. Spain is a little bit different, but is following some, or it's starting in the development of variable renewable sources, jointly with Germany. And I believe that the conclusions that we can get from these two countries, they can be useful for the nearly future in the evolution of the energy. My speech is about the role of the physicists. I'm not going to say what you should do in the future. I just want to raise awareness about certain problems that we'll see in the nearly future. And I believe that physicists, they could decide which research could be more useful for the society. Okay? Let's see if this works. This is the outline of my speech. Briefly, I'm going to talk a little bit about the current situation. Later, I will describe which is the plan for the following years, what is called the National Plan for Energy and Climate, the PNIEC in Spanish. Later, I will emphasize on the effect of photovoltaics and wind, but mainly photovoltaics will have in the system. And I will finish with a little bit about the market signals. Because the market, I believe, it's it's critical, because the market is the message that we receive from the whole system. Okay? As I said before, current situation, then high deployment of renewables, which are the only possibility to get rid of fossil fuels. And we know that Spain has a scarcity of fossil fuels. We need to import them. And the only opportunity is to promote the renewables. And later, I will talk about market signals. Well, I will start giving an overall image of how is Spain getting energy. The energy that we use mainly comes from outside. In this diagram, this is called a Sankey diagram. You can download it from Eurostat. It's not very difficult. We see that this is a horizontal band. On the left, we can see the origin of the energy. The upper part is the imports. the lower horizontal lines is the local production. We produce only two types of energies, nuclear heat, nuclear power, and renewables. And on the other hand, we need to import fossil fuels, mainly petrol and gas. The local production is about 22% currently. It's been quite similar during the last 10 years, maybe 15, but it's not been a burst in the production, in the renewable production. We are increasing, steadily increasing, but there is still a long run to be able to cover all the imports. Okay? Then the rest of the figure, you see that there is a line which is diverted. The one which is diverted below is that part of the energy that is being transformed in a secondary source of energy, mainly electricity. Or, for example, petrol that it's processed and converted in diesel and gasolines. We see that the renewables, they produce mainly electricity. Windmills and solar photovoltaics are electricity-oriented. Nuclear, 100% electricity. We release a lot of heat in nuclear power stations for security reasons. We don't make profit of the heat that is produced in the reactor and not used. We prefer to release to the atmosphere. About 2/3 of the heat produced in a nuclear reactor is released to the atmosphere. And 1/3 is converted in electricity. And happens in almost all power stations that. Okay, there's an opportunity to take profit of this, but we need to be careful because a nuclear power reactor is a critical facility. Okay, so we produce electricity, and electricity is the red band we see below. And this vector is supposed to be the substitution of all the fossil fuels. We still have a long work to do. Okay? And the rest is, Spain is also an important exporter of energy. We don't export electricity. We export mainly petrol, gasolines, because we process it here and we sell to third countries. And the right-hand side is that energy that we use in the industry, in our houses, everywhere. Okay, so with this image, I'm going to focus now on electricity, because it's supposed to be, and it's going to be, the opportunity to decarbonize and to shift from the fossil fuels. In this slide, I don't expect you to read all the figures. I just have highlighted or depicted several years and highlighted some values. If you see that the color is higher, it means that that value is higher than the one which is beside. And we see that coal, it's phased out. We'll see later how it was evolution, but it's out of the system. Nuclear power is still a steady source of energy. It's on top of that. Then hydroelectricity and combined cycle, they are very similar in terms of their capacity to respond to the system, and they are substitutes. And in the real life, both of them, they are fixing the price sometimes, and they fix with the same pattern. I mean, if there is a lack of water, then gas is going to be the substitution of water and the reverse. Okay, then we have the renewables. There's been a burst in the photovoltaics during the last 4 years, after a long period, we'll see later. And then we have the rest. Among the rest, the only one which is, let's say, relevant is the cogeneration compared to the rest, which is combined electricity production with heat production for a company, for factories, for utilities. Okay. There's been a little decrease. We can discuss later if you want. And now I want you to explain how I use two colors. The green one is the substitution between electricity and gas, which can be observed. And coal because it's been decreasing, and the renewables because they are increasing. In this slide, I want to clarify that not all sources are equally, they don't provide the same service to the system. On the one hand, for example, nuclear power stations are designed to provide a steady amount of energy during the 24 hours a day. It's very hard, it's difficult to model, to increase or decrease the power. So they are expected to be working at full power the whole day and night. This is what is called the base load production. Similar to the nuclear power station were the coal station, which also are designed to produce a steady amount of energy. They are very useful because they provide the base load, which is called a fixed amount of energy that the system requires. And then how we cover the difference between the base load and the real need using the following load following sources and renewable sources in between. The renewable sources, we allow them to get into the system, the first one, and then we cover the gaps using the load following. Load following sources, the main ones are hydroelectric and gas, combined cycles. So not all systems are substitutes. And we have to bear in mind that, because people believe that we can get rid of nuclear power stations and introduce renewables. We can do that, but we need to be careful, because the system will be more unstable. And we need to have additional systems to provide stability, to fill the gaps that the renewables cannot provide during some part of the days. Okay? That's I want you to remember that base load, nuclear and coal, load followings, we have hydroelectric, combined cycle, gas, and then the variable renewable sources like photovoltaics, solar thermal, and wind. They also have a significant contribution to the system. During the last decade, there's not been any increase in the solar concentrate or solar thermal, which I believe that it's a little bit, I would like to, Spain has the opportunity, is the country which has the situation where this source can be developed, because it needs a space with a big span of sunny days without clouds, and that happens here between Madrid and the south, but doesn't happen for example, in the Ecuador, because there they have, during the evening, they have storms, and that doesn't work. So I believe that solar concentrate, Spain should keep working on that area, because I think it has its opportunity. Okay, and cogeneration, I said before, that is slightly increasing. This is a picture of how was the breakdown of the different sources during a 24-hour period. To build this picture, we compute the median, the hourly median for the 360 days for each hour, and we split it in different. We see that it's clear what is base load. We see nuclear, we see cogeneration, we see coal, and we also see wind, which is providing energy during the day and the night, but with a high uncertainty. Here we cannot see that, but we'll see later that, as you know, that we cannot control the weather. And sometimes we have rain, and sometimes we don't have wind. The main idea I would like to highlight here is the difference that was between 2019 and 2021, that the main difference is in the gap, the layer of solar PV and hydro as well, because all the years are not equal. Okay, so I would like to say that solar photovoltaics is contributing positively, but we still have a lot to do to cover all the colors we see here. Because below the solar, is all the rest of sources. And some of them we want to get rid as soon as possible, like nuclear or those who rely on fossil fuels. Okay. This figure is showing, it's an observation of how it's been the historical for during 3 years of the correlation between the different sources. This is an empirical evidence. I get the data and I see what happened when one source is producing and another one. I have combined all of them. And also, I have introduced the spot price, which is the market in the auctions. How was the price? As we have price for each hour, I have depicted. We see the line, which is, if you count from the bottom to the top, the 4-1 is the spot price. If you see, here is very easy to read. If you see that we have a positive slope, it means that those two sources, they have a similar behavior. When one is increasing, the other one is increasing. If the slope is negative, they have a negative correlation. For example, we see that solar thermal and solar photovoltaics, they have a positive correlation, which makes sense. When one source is producing, the other is using the sun, and they have a positive correlation, both of them. We see, for example, where the pump consumption in the, I have not explained that, but I will go further, I will go deeper later, that when we are using energy to be stored, then the price tends to be low. Or when you produce using the power storage, it's because the price is high or because we need it, as we will see later. This is for Spain, and this one, I built the same for Germany. Why I choose Germany? Because Germany is, I think, is some years ahead of us. They have more deployment of solar photovoltaics, and what is happening in Germany, for me, is quite interesting, because it's what could be happening here in the following years. And I see that they also have interesting correlations. In this case, I have used only the central part of the day to build this correlation. So it's a little bit different from the previous one. I have just considered from the sunrise to the sunset. And because I want to see how is being the combination of solar photovoltaics with the rest of the system. And I see that solar photovoltaics, it has interesting correlations. For example, we see that with pump generation, it has a negative correlation. Makes sense. When we are producing solar renewable, then we try not to use it or we don't produce with the storage systems. We also see that the international balance, which is something that is here, I have not said before, in this system, that they are using the international connections also to compensate the effect of the solar photovoltaics, which is a bit controversial. I'm writing now a paper about this topic because Germany is surrounded by 11 countries, and that is very useful for them because they can send energy and they can receive energy more easily than Spain. Okay? We can discuss later, for example, biomass. They have an important source of energy with biomass. They are using biomass to compensate also the effect of the solar photovoltaics. Well, this is a little bit an image of how it's working the system in Spain. You know the different sources. I remind you that load following and base load are different, and both of them are needed in the system because we need to keep the equilibrium. And now, this is what is expected to be in the following years. This is the National Plan for Energy and Climate, what is called in Spanish the PNIEC. I have highlighted those figures that are expected to increase in the following years. This is the plan for 2025, which is very close, and 2030. High deployment of wind, high deployment increase of solar photovoltaics. This is in Spanish because I picked the picture from the PNIEC, from the report. We also see that pump storage is going to be increased. I wonder how it's going to be because it's about 50%. And this type of system, they require a lot of planning and looking for the right position, and also have a high environmental impact, because we need to build a dam at different levels, and we'll see later. Okay, carbon, coal is completely phased out, and storage was not present at the beginning, the first version of the PNIEC, and now they say that it's going to be 2,500 or 2.5 gigawatts of power of this source. They don't say how much energy could be stored. They just give the power plate or the capacity of the system, but not the capacity in terms of storage, which is important. It's going to be a storage system. I want to know how much is going to be, how much energy we can capture, and during how long, how much. Okay? This is the PNIEC. In the following pictures, I'm going to depict the evolution. This one is the historical evolution and the 2 milestones that we expect to reach in 2025, which is going to be next year, and in 6 years from now. The solar is growing exponentially now. There is a burst in solar power plants. But that's not happening in windmills. We are still going slowly in that direction. I think it's going to be difficult to reach the target of wind. Solar photovoltaics, probably yes, but not without some controversies or some problems that I think it's better to clarify now. Well, the following one is how was the evolution of coal. We phased out coal in 2019. That was the production during the previous years, and until 2021, it's completely phased out. The red line is a moving average, just to compute how was the median or the average during the previous 360 days. So in Spain, now the power capacity in coal is about 10%. The capacity was about 10 years ago, which is almost nothing. So it's a no return point. We cannot go back to coal. With coal, it's not very efficient. It's a high emitter of greenhouse gases, and I think it's a good idea to forget about this source. Okay, so if we get rid of coal, what has happened with the emissions? We have moved from an average of about 70 million tons every year to about now 40. That's the effect of coal. And depending on the year, if it's a rainy year, then we need less energy. The amount is going up and down slightly. But probably Spain will remain in that level during the following years. So we should try to reduce that, but I think it's going to be difficult to go below 40 or 30 every year. Okay, so if we are going to promote renewables, we know that they are weather dependent. What can we do? Because during the night, we don't have energy. We don't have sun. And for example, in summer, we don't have wind, which is happening, for example, today and yesterday. Spain is almost has no production of electricity from windmills. So the alternative is storage. Then I said, okay, let's read about storage and see how it's being used storage worldwide. I would like to know how much storage is worldwide. And then I looked for different articles, and I found one that gave me these figures. It was in 2019. It was difficult to find an overall image of the different storage systems. And this author, they say that the pump storage, which is used water to move it from a lower dam to an upper one, and then during the period where we need energy, we release the water and we produce electricity again. Okay, let's say, and we see that about 170 gigawatts worldwide were installed about these systems. Okay, let's see which is the following one. We found batteries. But the order of magnitude is 2 figures below. So there is a the horizontal scale is logarithm. So from 1.6 until 1.69 or 169, which is 100 times. It's a big difference. So if we are expected to store energy with batteries, we need to be aware that it's going to be difficult to reach now the level that pumped storage has worldwide. How this system works, okay? Later, I looked for more information, and I found that the International Energy Agency is providing figures for the following years. 2023, the figures are similar, are consistent with the one I found in this article. They say that the pump hydro, it's about 181, 169, which is not very different. The batteries now currently is about 54. It's expected to be in 2030. There are 2 scenarios. One of the International Energy Agency, they say that it's going to be about 600 in batteries. There are more optimistic 1 million batteries or 1,000. Pump storage is going to increase, but not exponentially. The figures is the brown. And okay, so if we are going to require storage of system, we need to be very skilled in these methods. I decided, let's see how it works, the storage of energy. Not difficult. I'm sure that you know how it works. We use during certain part of the day the energy to pump water, and later with the same system we produce electricity using like a hydroelectric system. Okay, I say, how does it work? I want evidence. Then I go to the regulator, I get all the data, and I split the data to build what is called a fan chart. This is showing me how it's been the deployment of this system during, you see, 4 figures during each season, because it's not the same. The renewable production is not the same in winter. I want to see how it works. That's why I split it in 4 figures. In each one of them, we have in the horizontal axis the hour of the day. And in both figures, on the top, we have the energy production. And the bottom, we have the energy consumption, the hourly. So we see that there is like both of them, the production and the consumption, they have bimodality. They say we are using it in the beginning of the day, we produce energy, store energy, and during the evening. And the consumption is during the night and during the mid part of the day. And that happens all the year. And I say, does it happen also in other countries? Let's go to Germany. And Germany is showing more or less the same, roughly the same. Here the modality is higher, probably the scales are different, but we see that pump storage is used more to provide load following service rather than storage. It was like the other day I was walking here near the beach, and we see that the sea comes up and down, the tides, twice a day. With the pump system, they happen similar. We are not storing energy during the night or during the day to provide it during the night. We are using it in a particular interval of the day. Okay? And they are using this because the system requires more following support. We can do it with gas, which is limited and is expensive, or we can do it with water. But water is also dependent from the weather or limited for the capacity of the storage system. And both Spain and Germany are showing the same patterns. You see the darker part is the central is near the median, and the lightest is the percentiles above, far from the median, the 10 and the 95 or 9%. Okay? So don't forget that we are using a storage system to provide stability rather than energy or storage. Okay, then let's see. If Spain is going to implement, to deploy more solar power, what is going to happen, or what has happened in the past? And here I have the peak, how it's been. This is fun chart. Every column is 1 year. Every row is 1 season. And this is the evidence from the data you can download from Red Eléctrica Española, from the regulator. In 2019, which is the first column, the amount of energy produced, or the output from the system was the one you see. Both, all the figures, they have the same vertical scale. Okay, so interesting things or two messages. Solar power, it is called a variable renewable source. It is variable, but has a part of uncertainty, which is how much energy is going to be produced today at 12 o'clock, which is the part you see in the middle of each of this curve, and it has a fully deterministic behavior, and which is the interval of hours where solar power is going to be contributing to the system. We know that today at 6:45, the sun was coming, and today at 21:45 will disappear. Today is 15 hours with sun. And that happens with switch clock precision. So we need to be aware of that. Because in every day, the solar contribution is going to disappear at a known hour. Okay, having this in mind, I depict this and say what is going to be the effect in the system. If I cannot storage the energy and I introduce this energy in the system, what is going to happen? What is going to happen in the following slide is that part of the demand is going to be covered by the solar photovoltaics. Okay. In the blue line, this is a picture built with real data from 2021. The thick line is the residual demand, which is the energy, the demand minus the solar contribution. In 2030, according to the National Plan of Energy and Climate and the deployment of solar photovoltaic, which is going to be possibly true, then we'll have that line, which is the brown one. So we see that the solar is going to contribute, but we need to discuss what could happen with this. And then I built the same fun charts with the solar photovoltaics. I found the same, that it has an uncertainty, but a deterministic behavior. So every day, we know that a particular hour, the sun will disappear. And for example, in summer, all the percentiles are very close. So almost the behavior is going to be the same. In winter, could be different, but we'll need a strong power of load following systems. Otherwise, the integration of solar photovoltaics is going to be difficult. This is what is called a duck curve. It's not very, let's say, academic, but it's a figure. It's just use the demand and then subtract the solar production. Okay, so let's see what is happening in the market now. Well, this is you are responsible of this. Okay, I was not sure to put these figures, but I will show it quickly. This is how it's been the price of the solar panels during the last 10 years or 15 years. The thick line is the median, and the shaded part is the 90 interval likely interval. We see that the levelized cost of energy with solar photovoltaics is going down. It's getting similar to the wind system, and this is very interesting because now we can build solar plants, which can be very small or big ones at a very affordable price. And that is going to contribute greatly to the system. The impact comes mainly from the modules, which are cheaper, much cheaper than used to be and more efficient. I think there has been done a great job, but it's time to focus on other problems. Okay, now just finishing, I said I would like to see how has been the behavior of prices during the past years. And I built, using the same code, I built these figures. And we see vertical, the columns are the years, and the horizontal, the rows are the seasons. We see that there was, during the 2019 and 20, prices were steady. In 2021, there was starting the discussion about how is the situation with Germany, with Russia. 2021, 22, the start of the war, and we see that prices went up. And we also see the bimodality. And the last figure is from the last term. The end of the years cannot be depicted because it has not happened. But what is happening now is prices are going nearly to zero during the central part of the day. And this is the price in the auction, not the price that the final consumer is paying for that. But it's the first price, which is going to be used later to build the price, the final price. So now, during the central part of the days, prices are going down. And I believe that this is due to the solar photovoltaics, which is, I think, is good, but we need to be, because it's showing uncertainty. And this is what is happening with Germany. If you want to see, I can share the presentation. And just to finish, some key ideas. Coal phase out has been supported by gas and solar. We should be aware of the needed, the balance we need between sources. We cannot say that with solar or with one source we can cover everything. We need to be aware that all the requirements that are needed to keep the stability in the system, load following sources mainly. And pump storage is useful for load following service than storage of energy. And we should pay attention to the market, because the market is sending messages. And if we keep introducing photovoltaics without storage or without an equal balance of storage and solar, then we might have problems with those companies that have invested and they cannot get the revenue that they expect. And with this, just to send the message, to finish, that hydrogen could be a potential solution, but we still have a lot to do. Because when we ask for the price of hydrogen produced using renewable energy and the price of hydrogen produced with methane, the difference is very big. And no one is going to produce, or no company is going to produce hydrogen unless they can get a revenue and a compensation for the investment. So, physicists, you have a lot to do with hydrogen because it could be a storage alternative. Look for opportunities in load following sources because solar photovoltaics are pressing us in that direction. And with this, I finish my presentation.
Hello, and thanks a lot for this. I'm here.
Hello.
Very interesting talk, really. My question is about the photovoltaics. You placed this plot, I think it's page 22 or so. With evolution, it was going down rapidly, And then the breakdown of the reasons why it was cheaper and so on. 22, I think.
I think the first one is 22.
Yeah.
22.
That one, thank you. It's really a mundane question, but in this lowering of the price, are there subsidies that are given by governments and so on taken into account?
This information I get from the report of Irena, and they get information from all the countries. And I assume that they are introducing subsidies as well, but subsidies don't continue forever. So they build, you see, this uncertainty interval based on the different values they get from different countries.
I see.
So this is a combination of all the, we should study this, but I want to summarize in one slide how has been the evolution of the solar panels. We say why solar photovoltaics is growing so fast.
So it's not just subsidies, the cells themselves are cheaper.
And this is the reason. The cells is the first one. It's responsible of about 50% of the reduction. The solar panels are much cheaper.
And a follow-up. So the price is going down, and it's truly going down. It's not just subsidies. Then I guess there are limitations in the way these things are built from materials or something. Is there like a showstopper for the evolution of solar panels? Not that you know.
I cannot assess.
So this can be scaled up, for the objectives of 2050 and so on, in your view.
I believe that prices they cannot be zero.
Sure.
They cannot be zero, and they should not be very different during the 24 hours a day, because I believe that energy is something that we all need it. And the government should introduce systems to show the cost of the system, but also to provide the proper compensation to the companies.
Sure. No, I was thinking more in terms of scarcity of materials that are needed to build them.
I don't think so, scarcity. Okay. Scarcity to build batteries, of course. But batteries, I found difficult to build batteries to use it at a utility scale or a country level scale.
But not the solar panels, those are fine.
No, I don't. Solar panels, they are going to be available, cheaper, and...
No worries. Thanks,
no problem.
Thanks a lot. Thank you.
Well, I have two rather economic questions, because you see that as a storage of energy, pumping energy is not good. But of course, there is a very economical profit, because you pump the water up when the energy is cheap and you release it when it's expensive.
That's what I thought. That's what I thought. But also, when I see, I have not mentioned a figure, which is below here. When you pump 100 units, you only recover 60.
Yeah, but much more expensive.
Much more expensive, but it should be a big difference.
I mean, it's not a matter of physics.
It's not a matter of physics, but the profitability of the cycle is not so clear. It's not so clear. And sometimes I think they use it, I'm not an expert, not in the system, the market, but they use it to control prices.
Yes.
To prevent, to go get energy from the system and to introduce energy in the system.
No, I was thinking also in the possibility, I don't know if this is real or some crazy fantasy, but the possibility of speculation. I hold the energy until it's expensive.
Probably.
And I have another question.
But speculation, I don't like that term. Because I will say arbitrary. Speculation is meant to long term. And arbitrary is to look for opportunities to, because I think those who build this type of systems, they should get the revenue they expect and they deserve, because they are contributing to the system. They do it for free. They don't do it for free. They do it for money. They should receive money.
And I have another question. For me, it has been surprising that combined cycle is expected to be the same for the following years. My idea is that it's due also to economical reasons. I think that it is due because these centers were built very recently. Is what I think,
The
but I
combined
don't know if
cycle
it's true.
is something that no one wants to say anything about them.
Oh, yeah, okay.
Okay? Because I believe that we need more combined cycle. And the combined cycle, they have a load following capacity, which is 50%. A combined cycle has two cycles, a gas cycle and a thermal cycle. The gas one, it works like a engine from an airplane that can, in very short, in seconds, they can go start very fast. But the thermal cycle, it takes hours. So if you see here about or the combined cycle 26, 26, 26, not all the 26 are fast response. And I believe that we'll need more in the early future. On the one hand, these are probably the cheapest systems in terms of capital expenditure. It means to install a new combined cycle is quite cheap. To run them, the OPEX, it's expensive. So I believe that in the early future, we'll see more combined cycles because we'll need it. And it doesn't take a lot of time to install one of them.
Yeah, thank you very much. I have a question because your statement on the combined cycle has struck me. We have double capacity installed that we need right now in Spain for power generation. Actually, this was a problem of the huge amount of combined cycles that we built by the beginning of this century. And the companies are pressing the government to be able of just turning down all the combined cycles plants from the system because we don't need them. That is, we have much more installed power capacity that we need right now.
I don't think so. There are certain times that we use the
So
full
the thing is
capacity.
that we actually have these plants, but many of them are disconnected from the system. So I don't quite understand the statement that we need more combined cycle plants to be built, maybe, but it will be enough with saying to the companies, okay, we need all these plants that we allow you to disconnect from the system to connect again. The second one is a question because your slide relies very much on renewable energies. And I have been working quite a lot on this, and I'm worried, for example, we are now in the middle of a heat wave, the first one, let's say, of this year, and the system is struggling with these extreme weather events. Not far from here, France is usually during summer having to turn down the nuclear power plants because of the high temperatures. They are not able of operating. And I would like to know if you know how this is possible to affect Spain also. Thank you.
We can discuss about this in the coffee break if you want, because I don't want to borrow time from the rest for the next speaker. But I think that combined cycles, we don't need to produce base load, but we will need it to produce load following. And companies, they also get revenues even though they have the system stopped, because they offer them and they get revenues for having the system ready to be used in the particular if needed. So companies, they always say that they don't make profit. Okay, it's the way to do the things, but we should see the long term and see if they make profit or not. Last question, or we stop here? We can discuss later. Okay, thank you.
Good morning. My name is Manuel Asorey. I'm Vice President of the Theoretical and Particle Physics Division of the Spanish Royal Society of Physics. And I have the honor of introduce the next speaker of this last day of the meeting, which is Alessandra Buonanno. Alessandra Buonanno is director of the Max Planck Institute for Gravitational Physics in Potsdam. She's also research professor of Maryland University in the States and PI of the LIGO collaboration in gravitational waves. So the subject of his talk will be about gravitational physics and gravitational waves. We were talking about revolutions in physics for the next decade during the previous day. And certainly this field of gravitational physics and gravitational waves is undergoing a revolution in physics. I mean, the astronomy, astrophysics will never be the same after the discovery of gravitational waves. Multi-messenger astronomy and astrophysics is just happening. And she will tell us for the first front line in this field about this, the latest development on the field. So just to introduce her, I will say that she is a theoretician in the analysis of a strong field, gravitational interaction, which is essentially the generating of gravitational wave in the catastrophic merging of binary systems, either black holes or neutron stars. And this field, as I said, is currently blooming, and this shows that, for instance, Alessandra has more than 400 publications, and each in this oscillating in the market every day, so it's about 125 today. But this is just to show in numbers the relevance of her research, sorry. And I will say that just to introduce her, that she started from PhD in Pisa University in Italy, not very far from here, but she moved as postdoc to Paris, the Institut d'Études Scientifiques at Bourg-sur-Yvette, but later on she went to Caltech as postdoc, came back to Europe, to Paris, to the Institut d'Astrophysics in Paris. But later on, she was tenured in the Maryland University, where still keeps the position, full professor there. But now, finally, as you know, she came back, was rescued by the Germans to the Einstein Institute in Potsdam. And she keeps going on this research in LIGO, and Lisa also is part of from the board of the next development of the field in the space. But also, all this activity was deserving many prizes and awards. She is member elected of the National Academy of Science, US, Italian Academy of Science in Italy, in German Academy of Science, Leopoldina, and many others. I don't want to borrow more time for her, but also I should mention that she has some personal prizes in awards in all countries, starting from Germany, where she got the most famous prize for research, which is the Leibniz Prize. But she also has the Dirac Medal from ICTP in Trieste, also Galilei Medal, and many others, which will not stop and will grow in the near future. I should mention that she, being part of LIGO, she was awarded a Spanish prize, which is the Princesa de Asturias, given to the collaboration, LIGO, where she is PI. And I don't want to take more time, but I would like to finish thanking her for coming here to our Bienal meeting. Thank you. Please come to the stage.
Okay, I hope you can hear me, right? First of all, I would like to thank very much the organizer and these very nice introductions for inviting me here. It's a real pleasure and an opportunity to talk to you about gravitational waves. So what you see here on the left is a still picture of a simulation that we did several years ago to represent the burst of radiation that was emitted by two black holes merging with each other the 14th of September 2015. In this short presentation, I want to, first of all, remind you what are gravitational waves, which unique information they bring us from the dark universe, how we decode the waveforms, how we interpret them and identify whether there are black holes, neutron stars, or something else. I will provide some highlights on the most recent results of the LIGO y Virgo collaboration. And I will also talk about the future. There will be new detectors, hopefully in the next decade, and certainly detector in space. And for that, you will see we will need to improve our theoretical predictions and also the data analysis methods. So let's start. Gravitational waves are a consequence or are a signature of dynamical space-time. They were predicted by Albert Einstein in two papers in 1916 and 1918. I wrote here the Einstein equation in full glory. And what Einstein did at the time was to linearize the equation with respect to the flat space-time. And in a particular gauge, he arrived to an equation of propagation of the wave that you might recognize a similarity with electromagnetism. If you were using the electromagnetic field, then here the current. So the waves are produced by the accelerated motion of mass. It could be matter, it could be just warp space-time. These are going to be our black holes. And as the body accelerates, they perturb the space-time around the source, and this perturbation propagates at the speed of light away from the source. And one of the peculiarities of the waves is the way in which they interact with free-falling bodies. In this animation, you see a ring of particles. This is a tube, and put the proper distance between the particles in the ring are squeezed and stretched because of the gravitational wave. And this is a highly accelerated effect of the gravitational waves on the Earth. Indeed, the waves are actually incredibly small, and in order to measure them on the Earth, they have to be produced by very big objects, like black holes and neutron stars. They have to be very compact because they have to be brought to very high speed without being disrupted. So a few words about black holes. They are just made of warp space-time. There is no matter. They come from the collapse of stars with a mass larger than 20, 30 solar masses. There could be also black hole produced by overdense region in the early universe. We call them primordial black holes. So we know that black hole is characterized by the horizon from which nothing comes out. And I want here to point out the fact that, so why we say black holes are compact, because if you take a black hole of 10 solar masses, the size of the black hole is more or less 30 kilometers, and you can contrast that with the size of the sun, which is 700,000 kilometers. So black holes exert a very strong pull around them, also bending light from stars or galaxies that are around. So now a few words about the fact that black holes are also, quite surprisingly, the simplest object in nature. They are only characterized, the astrophysical one, by two numbers, the mass, which determine the size, and the spin or rotation, which determine the shape. So now a few words about the neutron stars. They also come from the collapse of stars, but smaller than the one that produce black holes. And their mass is limited to around 1 or 2 solar masses, and the radius it's in this range. And neutron stars are also compact, but less compact than a black hole. I also want to point out that black holes in the universe come with different sizes. The one that LIGO, Virgo, Kagra are discovering are so-called stellar object black holes, stellar mass black holes. They have a mass between 10 and 100 solar masses. But we know that there is a black hole at the center of our galaxy, Sagittarius star, 1 million times the mass of the sun. We know quasars with 10 billion mass, the mass of the sun. And these especially big black holes play an important role. They are at the center of galaxy. They have an influence on the galaxy, but also on the cluster of galaxies other galaxies that belong to the same cluster. Or black holes, hundreds of thousands solar masses, are part of globular cluster, and they determine the evolution and even the life of these globular clusters. Now, one of the open questions is how these big black hole form. Two mechanisms are proposed. One is accretion of gas that increase the mass. And the other, if you have a black hole at the center of galaxy, the galaxy merge with each other, and in this way, over time, you increase the mass of the black holes. Okay, now a few words about the strength of the gravitational wave. I drop all indices, although the strain or the amplitude of the wave is a tensor. Einstein found that the strain is proportional to the second derivative of the quadruple of the source that produced them. So if you have a binary system, you can actually compute the quadruple for a binary moving on a circular orbit, where v is the velocity, and you get this formula. M is the total mass of the binary, so the strain is proportional to v divided by the speed of light to the power 2. It's inversely proportional to the distance, as you have in electromagnetism. So it will be very nice if there are many mergers of black hole and neutron star in our galaxy, because we will detect them very easily. Unfortunately, these are very rare events. And so to detect these systems, we have to build detectors that are sensitive to a very large volume that include many, many galaxies. Now, if you consider a binary neutron star in the Virgo cluster, which is the closer cluster to us, which has of the order of 20,000 galaxies, you get this number, which is incredibly small. But if you compute the power, the luminosity, the energy per second, you just take one derivative of h and you square it, you get at leading order in an expansion in v over c this quantity here, okay? C to the power 5 divided by g, it's an enormous actually power. It's 10 to the 23 times the power that is emitted by the sun in electromagnetic radiation. And this power, in fact, is similar or larger than the one of the all-visible universe. And another important feature is the fact that once the waves are emitted, they travel up to the Earth, and they are almost unaffected by whatever they encounter. Although at the end of my presentation, I will tell you that there are some effects, like, for example, gravitational lensing that we have to care about for the future. Okay, so in order to detect a wave, detectors have been built. These are laser interferometers. You see here the picture of the LIGO, Virgo. There is a detector in Japan called the Kagra. And detectors use this, the key idea that is used to detect the gravitational waves is the way in which they interact with free-falling bodies, which in the case of interferometers are the mirrors that hang by wires at the end of the Fabry-Perot cavities that are free of moving above a few hertz. So what this detector measures is the differential mode of motion of the mirrors. There is some light that leaks out from the beam splitter, from the dark port, and in order to measure something of the order of 10 to the minus 21, we need this kind of precision in the measurement of the mirrors. Now, I will focus on binary system, and for binary system, we have a luxury. We can predict the signal in advance, as we will see from the theory of Einstein. And so the best way of detecting them is using match filtering or signal processing. And I have a little animation here. In black, there are the data, hopefully with a signal. You slide the template, which is in pink here, and you maximize on the parameters of the binary. And when the signal-to-noise ratio, or this correlation, is higher than a certain threshold that has been set depending on the knowledge of the noise in the detector, we can claim a detection. And we need, for the bank of templates, 100,000 of waveforms of templates. We need millions of them when we do follow-up analysis to extract the parameter, when we do our Bayesian analysis. Okay, so let me go back to this formula. I was telling you about the amplitude, okay? But if you use match filtering, what you care is the phase. You have to get the phasing very, very accurately in order not to miss the signal, or maybe to reduce too much the signal-to-noise ratio. So how do we get the phasing? I will give you just a very simple explanation here. So first of all, from the quadrupole formula, the phase of the gravitational waves is twice the orbital phase. Now, how we get the phase? On one side, you have a binary. There is a binding energy associated to it. At leading order, you can use just Newtonian gravity to determine the binding energy, which I wrote here. Then you need the luminosity at infinity. The emission of gravitational waves bring energy that goes away. And this is the formula that was predicted by Einstein, although at the time he was not thinking about binary systems and black holes, but he derived the formula in the most general way. And then you just say, okay, there is an energy balance equation. The variation in the energy has to be equal to minus the flux at infinity. And if you take a quasi-circular orbit, everything depends on omega, the frequency. So you can rewrite this equation in the following way, and then you integrate and you get basically the phase. So the two important ingredients are the flux and the energy that you have to determine very well by solving the so-called two-body problem in general relativity, as I will show you in a moment. So we detect the signal with match filtering. We want to extract the parameters, and this is the most important thing. So the waves are fingerprints, we say, of the source. All the parameters of the source are imprinted in the waves. And although we use Bayesian analysis, I want to just show you how they are imprinted. For example, you see here the frequency of the wave is increasing over time, then they merge, the two black holes, and there is a new black hole that forms at the end. From the frequency evolution, we can infer the masses. If we get the amplitude and the masses, we can infer the distance to the source. If we record at the different detectors the time of arrival, the amplitude and the phase, we can reconstruct the location in the sky where the event happened. Now, this waveform is for two black holes going around on a circular orbit, okay, non-spinning. The black holes are non-spinning. If you include the precession of the spins, or the orbit is not quasi-circular but is eccentric, you get modulations in the signal of this kind. And so if you can detect them, you can learn whether the two bodies were actually moving on an eccentric orbit or they had some spin. If you consider a binary neutron star, the signal is quite different, not just when the two neutron stars merge with each other, but also before that, because the neutron star can be tidally deformed by a companion, and that deformation depends on the equation of state of the neutron star. We will see it in later. But here I wanted just to point out that there are differences between a binary black hole and a binary neutron star, even with the same parameter, because for the black hole, this deformation, this tidal deformation is 0. Finally, you can compare the waveform with theory of gravity, which are not general relativity, and you can probe. The theory of gravity is in the strong field, general relativity is still valid. Okay, so in order to solve this problem, we have actually to take advantage of the Einstein equations, and we have to solve them in two different ways, analytical and numerical. And I want to make here a similarity. So I want to start with the Newtonian gravity that perhaps everybody here knows. In Newtonian gravity, we have a formula that describes the motion of the planet around the sun. Unfortunately, there is not a closed form that describes the orbit of two black holes going around each other, because the Einstein equations are nonlinear and are very complicated. And in fact, the ellipse, as you know, first of all, precess. No? Remember the precession of Mercury, okay? Like in this example here, this is actually the star going around Sagittarius as star, as you maybe know that we have done studies to actually follow the small star going around the black hole at the center of our galaxy. But this is just showing you that the ellipse is rotating. And if you include the effect of gravitational waves, the ellipse not only precesses, but also shrinks over time. So we cannot solve this problem exactly in closed form. And so we have to work with people who do simulations on supercomputer, which solve this equation numerically. Now, let me be a little bit more precise. So first of all, the supercomputers are used because it's very time-consuming to produce a numerical relativity simulation. I have one here. So what you see here is the flux, is the energy per second scaled to the one of the sun in electromagnetic radiation produced by two black holes going around each other on a generic orbit. And here you see the polarization of the waveform, H plus and H cross. The primary black hole has a spin, and so the orbital plane is actually precessing, and this is why the maximum radiation in this plot is not always in the same direction, but is moving, because of the orbital plane is precessing. It takes from a few weeks to 6 months or more to produce one of these simulations for just 15, 20 orbits, okay? And I told you we cannot solve this problem just with, in this way, because we need hundreds of thousands or millions of templates to analyze the data. So what we do is that we use, of course, numerical relativity, but we make use also of solution of the Einstein equation, which are approximated, analytical. And the oldest one is post-Newtonian theory, which was introduced, in fact, originally by Drosten, Lorentz, and then Einstein, Infeld, and Hoffman. So you expand the Einstein equations in powers of V over C, or Gm over RC squared, where R is the separation and M is the mass. And so this is a weak field, low velocity approximation, which is valid when the two black holes are quite far from each other, and the velocity is still small. But I remind you, close to merger, the velocity is almost the speed of light, okay? Then one can use post-Minkowskian approximation. You expand the Einstein equation in powers of G or G over R, so it's a weak field, but it's at all orders in the velocities, which can be used in particular for large eccentricity or scattering. Or you can expand the Einstein equation just in the mass ratio, so this will be strong field, but you can apply it when you have a small body going around a big body. And these are sources, especially for detectors in space, as you will see. Then we can put together these different approaches in a formalism that is called effective one-body theory, which also offers some physical, uses physical ansatz for describing also the merger and the ring down. And this is actually improved by calibration to numerical relativity. But we can also build frequency domain templates. They are called phenomenological, and they are built by putting together the effective one-body approach, post-Newtonian, numerical relativity. They are very efficient because they are built in frequency domain, and I will say something more also later about that. So I have one slide to show you how we put together this method. I told you calibration to numerical relativity. What does it mean? So we start from a waveform, an effective one-body waveform, which has some dephasing with the numerical relativity waveform. You can see at the beginning, when they are very far from each other, there is very good agreement, but then some dephasing accumulates, and we want to reduce that dephasing by introducing calibration parameters until the waveform agree with each other. And we repeat this process for many numerical relativity waveforms at our disposal. For example, in building the most recent effective one-body numerical relativity model that we developed in our department, we use 441 numerical relativity simulations that are represented in this plot here. This is the binary combination of the spin, and this is the mass ratio. The different colors correspond to the different mass ratios. Now, these waveforms are used on one side to build a template bank. This is the projection of the template bank in the mass plane. At low masses, we use plain post-Newtonian waveform of the order of 75,000. For neutron star black hole and black hole, we need these few hundred thousands of effective one-body numerical relativity waveform. And there are, as I said, other waveforms used by the LIGO y Virgo collaboration, in particular this IMR phenom, and waveforms that interpolate directly numerical relativity when they are available. Okay, so let me show you now, once we have these templates and we have a signal, what we do a Bayesian analysis. We are matching our templates against the data, and we do it by changing the parameters. So here is the very first event in blue, and the template is in orange. By changing the distance, by changing the mass, we try to find the best solution against the data, And once this is done, we know the distance of the source, the masses, even we can reconstruct the final mass of the black hole that formed after the merger, how much it was rotating, 70% of the maximum value. But since we are physicists, what we do is that we produce posterior distributions. The waveform depends on 17 parameters, so many. It's a higher dimensional parameter space. When you marginalize on all the parameters except for the masses of the black hole, you get the posterior distributions here, which agree very well between the two state-of-the-art model, EOBNR, and this IMR phenomenological one. Okay, but what happened in the last 9 years, and, since the first discovery of 1509-14? Well, almost 100 events have been discovered. We represent the event in the stellar graveyard. So these are all in blue, the black holes that were observed by LIGO and Virgo. The way of reading this plot is that you have one black hole that merges with another black hole and form a new black hole. In orange, you have the neutron star discovered by LIGO and Virgo in form of a neutron star black hole or two neutron stars. So I will highlight a few events that I will describe. The first binary neutron star, 170817, the largest black hole system observed until now, with the masses around 100 solar masses. The LIGO collaboration detected two events a little bit puzzling because one of the two objects has a mass which is too high to be the mass of a neutron star, perhaps too low to be the mass of a black hole. So we don't know actually what it is. And I wanted to highlight just last April, as part of the ongoing run called O4, a first discovery paper was published by the LIGO and Virgo and Kaga collaboration. This is a neutron star black hole discovered the 29th of May, 2023, and I will say something later. And the current run, which started last May and will end next June, has already provided 117 signal candidates. The papers are not yet out. So this number will add to this, large number of observations that have been done until now. So let me show some highlights. So the 14th of August, 2019, a binary was discovered where the secondary mass has a mass, as I was saying, a bit too large to be the one of a neutron star, which a neutron star has generally a mass up to maybe 2.2 solar masses, and perhaps too small to be the one of a black hole. But the peculiarity of this event was the mass ratio, which you can see is around 10. And the more substructure, more asymmetry you have in a binary, in the masses, in the spin, the richer is actually the signal. And this simulation that we did in our group represents the event, the gravitational wave, the total one, but as the two bodies approach each other, the higher harmonics become important. So there is the dominant harmonic coming from the quadruple formula, the quadruple emission, but then you can start having the octuple harmonic. So you see the L equal 4 here, and then the L equal 5, very close to merger. These harmonics become more and more important as the two bodies approach each other. Now, what I wanted to highlight is that only when we include in the waveform physical effects like the presence of these harmonics, higher modes, and also the precession of the spins, we can get a posterior distribution for the secondary mass, which is quite tight. And this is by including the precession and the higher harmonics. Otherwise, the posterior distribution would be much broader. We wouldn't get this very good determination of the mass with an error around 10%. So let me go now to the event discovered the 21st of May, 2019. This is a visualization, numerical relativity visualization of the event. This is the largest binary black hole observed so far. And the puzzle here is the mass of the black holes, in particular the mass of the primary, which is 90 times the mass of the sun. And the reason is because astrophysicists tell us that there is a phenomenon called pair instability supernova that would prevent to see black hole from the collapse of star between 60 and 120 solar masses. So where actually these black holes could come from then? When one possible explanation is that they were secondary generation black holes. So what I mean is that they could have been formed from not a collapse of a star, but a previous merger of two black holes. Then you have a black hole that wanders around, and then at some point, encounters come so close to another black hole to be dynamical capture. So this could be a possible explanation. Okay, so once we have this event, we can also do tests of general relativity. And this is something new because it's done in the so-called strong field, high velocity regime, which is not accessible, for example, in the solar system or even in cosmology. And I want to mention just one test. The black holes, I told you at the beginning, they are the simplest object in nature. And if you perturb a black hole is like a bell. It emits gravitational waves, if you perturb them, at specific frequencies. Or if you want frequency, real part and imaginary part. They are called quasi-normal modes. Now, this is, again, a visualization of the very first event. So in that last part, when the black hole merge, you form a new black hole, which is a bit deformed. And as it goes to the stationary configuration of a Kerr solution, it emits this damped sinusoid. Now, you are familiar with the fact that electromagnetic spectral lines can identify chemical elements. Well, there is an analogy. The quasi-normal modes of the black hole can identify the black holes in general relativity. They only depend on the mass and the spin of the black hole. And so if you can measure more than one mode, you can basically put at stake general relativity. You can understand whether they are consistent with the quasi-normal mode of general relativity, or maybe the theory of general relativity is violated. So since you didn't hear any news about general relativity being violated, I'm just going to report that general relativity has passed the ring-down test and many other tests that both the collaboration and independent analysis have done so far. Okay, so now let me tell you a little bit about binary neutron stars. So the binary neutron stars that LIGO and Virgo have discovered, so in particular the 170817. So a neutron star is also a very peculiar object. I told you already has a mass between 1 and 2 solar masses. We don't know the composition of the neutron stars, in particular in the core, where the density can be a few times nuclear density. And I mentioned to you that the neutron star at the beginning, I mentioned to you that it's characterized by a parameter which is called the tidal deformability parameter, which actually describes the ratio between the quadrupole moment induced on the neutron star by the companion, due to the external tidal field of the companion. This parameter is 0 for black holes. And this was just the cartoon that I showed you at the beginning. By observing this dephasing, we can actually extract information on lambda. And by doing that, for 170817, one could bound the pressure and the density of the neutron star at different levels of confidence, statistical confidence, even at twice supernuclear density, as you can see in this plot. And also the measurement led to the fact that we could say something about the radius of the neutron star to be around 12 kilometers. But this event, as was also said during the introduction, opened this field of multi-messenger astronomy with gravitational waves. 2 seconds after the event, the Fermi satellite detected a short gamma ray burst. So this is the track from the LIGO and Virgo observation, and this is actually what the satellite Fermi observed and also integral. 11 hours after the collision of the 2 neutron stars, the source was localized in the sky, and several optical telescopes looked in that patch of the sky and identify a little object that was close to a galaxy which was not present 20.5 days before. So that was localized as where actually the event happened. So this event was followed in X-ray, infrared, radio even for a couple of years. It allowed an independent measurement of the expansion rate of our universe, and also allowed, by looking at the gravitational wave and the GRB, the short gamma ray burst, to nail down the speed of the gravitational waves with exquisite precision, as you can see here. Now, you may wonder, we saw two neutron stars, black hole binaries. What about the mixed objects? Neutron star black holes, these were discovered, the very first robust one, the 15th of January 2020, and this is a visualization of the event. Because of the masses of the black hole and the neutron star and the spin of the black hole, in this case, the neutron star is swallowed by the black hole, leaving basically no accretion disk. But in the future, we might observe, depending on the parameter of the binary, an electromagnetic counterpart because an accretion disk could be formed after the merger of the two events. So let me then finally tell you something about the event published in April, and then I will wrap up with the future. So this is an event that was discovered the 29th of May 2023. Has been called a mysterious object because in this plot here you have the mass in solar masses between 1 and 6, and previous event had started to populate this range here. I told you about 190814, okay, this puzzle object. There was also another binary neutron star. This was actually the neutron star black hole I was just talking about. So this system is composed by certainly neutron star, but the black hole, it's peculiar because we thought, astrophysicists thought, that there are no black holes in the range between 2 and 5 solar masses. But this was coming mainly from the fact that the black holes in our galaxy, that we see in X-ray binary, were not observed in this range. But this maybe was an observational bias. And this is the first example of a black hole squarely in the so-called low mass gap. Okay, this is a visualization of the event that we did. You can see here in particular the masses of the two objects, and now the neutron star is disrupted and swallowed by the black hole. Okay, so I will skip this plot because I want to go now into the future in the next 7 minutes. So the future is very bright. We hope to have new facility on the ground, the Einstein telescope in Europe and Cosmic Explorer in the US. And these detectors are going to increase the reach at which we can see this binary black hole, neutron star, and maybe other gravitational waves from other astrophysical objects. So this plot shows you the distance in redshift at which we can go with this new detector compared with LIGO, which is here. And this is the mass of the total mass of the binary. And you can notice that because these detectors are going to be sensitive more at low frequency, so the reason why we don't see black holes with LIGO and Virgo of 1,000 solar masses is because they merge outside the bandwidth of the detector, which starts at 20 Hertz. If you bring the bandwidth more at lower frequency, you start seeing also black holes of 1,000 or few thousand solar masses. And going at this large redshift, we will be able to see perhaps black holes, primordial black holes, because we will go at the time that, you know, if we see a compact object dark, it cannot be a black hole from a collapse of a star because there are not stars at that time. This is before the so-called cosmic dawn in our universe. Now, it's quite overwhelming to think at the number of events that this detector will have. So in 1 year, we could have 10,000 binary black holes with a signal-to-noise ratio of larger than 100. Today, the signal-to-noise ratio is typically between 10 and 20, so it's 1 order of magnitude more. And we might see of the order of 500 binary neutron star with a large signal-to-noise ratio, so we will nail down really the equational state of the neutron stars. We will have a detector in space next decade. It has been recently adopted last January by ESA, so it now is under construction. It's a constellation of 3 satellites going around the sun behind the Earth. And LISA will open a new bandwidth around the millihertz. And this is the noise spectral density of the detector. There are many sources here. I wanted to focus on the massive black holes, massive black hole binaries. The tracks are here. The color corresponds to the signal to noise ratio up to more than 1,000. And they will last in band for weeks or months. And these are the black hole of million solar masses at the center of the galaxy that at some point form a binary system before they merge with each other. We will see extreme mass ratio in spirals. The tracks at different harmonics are here, with a small object going around a large object for millions of orbits, probing the spacetime around the black hole with exquisite precision to do tests of general relativity. We will see many white dwarf binary in our galaxy, and surprisingly, there will be also multi-band sources. A binary black hole that starts to be seen in LISA band, and after a few months or a year, will be seen with a facility on the ground, like Einstein Telescope and Cosmic Explorer. Now, these detectors, including Einstein Telescope Cosmic Explorer, they put really new challenges in terms of data analysis and also in terms of theoretical predictions for the models because of the large signal-to-noise ratio. So I wanted to give you two examples. We will have so many events, for example, with Einstein Telescope, that will be very important to analyze them very quickly. And of course, one of the methods that can be used that people are exploring is to apply machine learning. We developed recently a code called DINGO with the Max Planck of Intelligence System, which is able to analyze actually data like the very first event in just 10 seconds. This is the posterior distribution of DINGO compared with the standard one produced with Marco Chain Monte Carlo that will take up to a week depending on the waveform model that is used. For the data analysis of LISA, this problem is incredibly complicated. It's called the global fit. And the reason is the sources are not going to be just temporary, like in LIGO Virgo, just lasting for a fraction of a second. The many sources are going to be there all the time. And so it's a problem where basically, generally it's represented with a cartwheel. So you have some data. You have to start, first of all, detecting the largest, the loudest events, which are the white dwarf from our galaxy. Then you subtract them from the data. You look for the next source, the supermassive black holes, and then you subtract them, and you look for the next one. And you repeat this as you continue to observe, because the signal-to-noise ratio is increasing, because I told you all this data and the signals are there all the time. So this is something that needs to be developed for LISA. So basically, there are important advances that we have to do. In the theory, we have to improve the waveform models that we have today by at least 2 orders of magnitude. We have to improve the accuracy of the numerical relativity simulations. We have to include all possible physical effect in our waveform, because we will be so precise that even the presence of a third body on a binary could be actually imprinted in the waveform. Or the fact that the binary is not in vacuum, but for example, is in an accretion disk around the black hole. I told you at the beginning that we should not care about the fact that the waves are produced somewhere and then they pass, they cross the universe and arrive to us. Well, with these detectors, we have also to care that they could be distorted through the phenomenon called gravitational lensing. You know this phenomenon for electromagnetic astronomy. It produces multiple images. Maybe you have seen them in some plots. Well, if this is LISA and this is a source, and you have a lens, depending on the mass of the lens, the signal can be distorted. The distorted signal is in color here. The unlensed is in black. And in fact, you can even have multiple signals which would correspond to these multiple images. Okay, so I now finish. Yes, this is my last slide. So I hope I convinced you that the work at the interface between analytica and numerical relativity was very important to detect, is still very important to detect the signals, but also to interpret, to extract information and of the astrophysical and cosmological sources with a greater accuracy and of the upgraded and future facilities come the even greater challenge for theoretical gravitational wave modeling and data analysis. This plot shows you the cumulative detections for signal-to-noise ratio larger than 10 as you go from the fourth run, which is where we are now, the fifth run, the upgrade of LIGO and Virgo, and then Einstein Telescope Cosmic Explorer. And this is for LISA. And by the way, this is the signal-to-noise ratio for an event like the very first one, which was around 24, and that this event would be seen with a very large signal-to-noise ratio in the future. And so for that, we have to include physical effects, improve the accuracy of the waveform models if we want to avoid making wrong scientific statements. And so this will be very important. There is a lot of work to do, and perhaps some of you will be excited to work in this area. I want to thank my group. A lot of work I presented is also, they contributed very much. And also the LIGO Virgo ECAGA collaboration and the LISA consortium and the Einstein Telescope collaboration. Thank you for your attention.
We have time for some questions, comments. Go ahead.
Hi, hello. First of all, thank you for your talk. It was really educational for me. I have a couple of questions. Maybe the first one is a little bit basic, since I'm not formally trained in general relativity. But you said that, for example, from the frequency of the waves that you detect, you can infer the mass of the object that created it, right?
Yeah.
Well, if I'm not mistaken, because of the expansion of the universe, electromagnetic waves redshift when traveling through space. Is this also true for gravitational waves?
Yeah, so indeed, thank you for the question. So what we measure is actually the redshifted masses. So it's the mass of the object multiplied by 1 plus z. But then we assume a certain cosmology model. And so because we get also the distance, we can basically measure the redshift, but we have to assume the cosmology, because the gravitational waves by themselves, they don't give us access to the redshift. And so once you know the redshift, then you can compute what we call the source mass. So sometimes in the papers you read the source mass and the detector mass. The detector mass is 1 plus z multiplied by m.
Okay, thank you. The other one is maybe more related to the data modeling and fitting that you mentioned. You said that you're implementing machine learning tools in order to accelerate these processes. And in this conference, there has been a lot of talk about new type of computing, like maybe quantum computing. Do you think that could also help in your calculations?
Well, of course, I was not at these talks in particular because I arrived only yesterday. Of course, they can help in, so the way in which machine learning was used in that, inference analysis is not in producing the models, but is in, so we use normalizing flow to basically produce, use a method that at the end doesn't need a likelihood function, if you want. Mm-hmm. And so this allows at the end to accelerate the way in which we do the inference. And if that can be done also, with quantum computers or quantum computing in general, that will be very nice. From the point of view of the waveform, the prediction of the waveform, until now, although people have been thinking, can we solve the Einstein equations maybe in a way that is different from what we do today and make the solution much more faster than what is done with numerical relativity, I have not seen any concrete example of that, but could be interesting.
Thank you.
Any other question? Yes.
Hello, I have also a very simple question, a general physics question. I'm thinking in my students of first year. It's because you say that the precision of the measurement is 10 to the minus 16, but that's impossible, I think. I think that that's the precision of your fitting parameters or something like that. Because you make a fit of a theoretical waveform to your experimental data.
Okay, no, yes, maybe if I understood the question. So the 10 to the minus 16 centimeter was the precision of, measuring the displacement of the mirrors. But that is not, so once you have, so you do your detection, then you know that there is a signal, and then we match basically the signal with templates. So this is what we are doing. And the precision actually is not at all 10 to the minus 16. The precision, in some cases, it's a few percent, or it can be 10%, 20%. At the moment, it's not. In fact, the measurement accuracy is basically the inverse of the signal-to-noise ratio. And because we have a signal-to-noise ratio typically of 10-20, it's around 10%, etc. That's the kind of accuracy that we have today. But in the future, this signal-to-noise ratio will become 1,000 or 10,000, and there we will have a better, accuracy. But it's not 10 to the minus 16.
So thank you very much. My comment actually, or question was actually in the same, from the same point. I mean, it takes a lot of confidence from the community, and especially also from the theorists, that after 30 years, because I remember when I was presenting my PhD in Germany, they asked you general questions, and they asked me how to measure a gravitational wave. I remember. Okay. And there was a PRL that I was just reading before, and they were talking about gravitational waves, right? That was year 1985. Okay, but what I think is this 10 to the minus 16, which is how you can control the position of the mirrors in the interferometer, is amazing, right? And as you mentioned, the signal to noise will increase, but I am wondering what is going to be increased there, what is going to be improved? Is the correlation between LIGO and Virgo, or is just the instrument itself, yes. Or how are you going to increase the signal to noise to orders of magnitude that you're talking about?
So the interferometers are, let's say for the ground base, right? Because space is a bit different, but let's say Einstein Telescope Cosmic Explorer. So first of all, the typical curves of these interferometers are characterized by mainly three sources of noise. And I want to go back a moment to the plot I had here of the noise spectral density of the detectors. So when you see this noise spectral density here, so here is basically the shot noise in the laser interferometer, which you can bring down with more power. If you increase the power, you can bring down them. But of course, it's not easy to also increase too much the power, because you lose also the control of the mirrors. So for example, people have developed squeeze light, also frequency-dependent squeezing, not just frequency-independent one. And so that you can reshape, you can bring actually this down with squeezing and increasing the power. Here you need a better seismic isolation system, because this is basically the seismic noise here. So the mirrors hung by wire, so you have to improve, the low frequency in that way. And at some point at low frequency, you start touching the so-called gravity gradient noise. This is due to fluctuation in the Earth, inside the Earth, that then couple with the mirrors. It's like tidal effects that create a noise. And in fact, this is one of the reasons why, for example, the Einstein telescope, which wants to have a very good sensitivity at low frequency, wants to be underground, so that you can try to screen this kind of noises. But at some point, you cannot do anything. That's why you go to space, if you want to go to the million. This region here in the middle is the thermal noise, of the mirrors and the suspensions. And for that, the Kagra detector in Japan decided to go into cryogenic, although they have not yet, implemented it. But there are also materials that you can use for the mirrors. These are generally sapphire mirrors are made of sapphire that can reduce this, thermal noise. So these are all things that will be implemented in order to increase. And actually, I have to say also the length. So these are 3 kilometer, 4 kilometer interferometer. You also can bring the noise down if you increase the length. In fact, it's just from this formula if you want. Sorry, this formula here tells you that if you want to achieve with the same H, if you increase the length L, you achieve a smaller delta L, or you see what I mean? So these are all things that people are developing in order to improve the sensitivity.
Any other question? But I do have.
There is a question.
Oh.
Hi, thank you for the talk. I also want to go to the basics because I'm not.
But by the way, these are not basic questions.
Well, okay, but you know.
Okay.
I'm not talking about the detectors or anything. But why the signal is different, especially in the end, for neutron stars and black holes? Like, what is the intuition of the
Yes, very
signal?
good. Yeah, it's not an easy question. So it's different because, let me go to that. So when you have two black holes, and they merge with each other, and this you saw in some of the movies is very fast, the last part, then you form a black hole. I mean, there is nothing else you can form. And so at that point, you have a black hole that is a bit deformed. It continues to emit gravitational waves until it goes to this configuration, which is axisymmetric. It rotates because of the angular momentum of the two objects, so it has to preserve the angular momentum. So it rotates, and at some point, it doesn't emit anymore. If you have two neutron stars, it's not obvious the outcome. It can be a neutron star, it can be a black hole, what forms after the merger. It depends on the mass of the neutron star, because I was telling you the mass of a neutron star is between 1 and 2.1 solar masses. So now you see that if you want to produce a neutron star, the masses of the neutron star have to be small enough that the final one can be a neutron star and not a black hole, because if the mass is larger than 2.2 at the end, it cannot be a neutron star and you have a black hole. Moreover, when they actually merge the two neutron stars, what happens, people have seen in simulation, is that you form first what they call an hypermassive neutron star. So you form an object which is unstable, it's rotating, and that rotation is producing all this kind of monochromatic, it's not actually monochromatic, but this monochromatic signal. And then at the end of this process, it just collapses to a black hole. In this particular case of this waveform that I show here. So if you want, there are two things. You can have an intermediate phase of this hypermassive neutron star, which then collapses. And then you have the fact that it can go either to a neutron star as a final object or to a black hole as a final object. Okay? So it was not a basic question.
Thank you very much, Alessandra, for your talk. And we have to close because we have to move on. And let's thank again.